Hey there, awesome physics students. Let's talk about angular momentum. We're going to build up angular momentum in direct analogy to regular linear momentum. So let's talk about the components of linear momentum. First, linear momentum has the velocity included in it, and velocity is a vector. And the rotational version of velocity is omega, the rotational velocity, or the number of times it turns around in a second. Of course, omega is going to be measured in radians per second. Regular momentum also includes the mass, which represents the inertia of the object. The quantity that represents the inertia in rotational is the rotational inertia, or the moment of inertia, I. And remember, I tells you how the mass is distributed around the axis of rotation. So if the mass is distributed far from the axis of rotation, I will be large. And when the mass is concentrated closely to the axis of rotation, then I will be small. The regular momentum is just the mass times the velocity. And of course, regular momentum is a vector, and it gets its vectorness from the velocity vector. The angular momentum, is going to be composed in a very analogous manner. We're just going to take the rotational version of inertia and the rotational version of velocity. And L is actually a vector as well, and it gets its vectorness from the angular velocity vector. And you might say, well, what direction does angular velocity point in? Well, if you have an object, let's say you have a disk, and it's rotating through an axis of rotation, the angular velocity vector points along the axis of rotation. We might say, well, then does it point up along the axis or down along the axis? We need to decide which direction it rotates. It points. So if you take a regular object and it's rotating, you take your right hand, and I'm going to use my left hand because this video is mirrored, so to match yours. But you take your right hand and you curl it in the direction that the object is rotating, and then your thumb points along the direction of the axis that determines the angular velocity vector. So in this case, the way this is rotating like this, the angular velocity vector points down. If it rotates the other way, then you again take your right hand and curl it in the direction the object is rotating, and your thumb points along the direction of the angular velocity vector. And that is going to be the same as the direction of the angular momentum vector. They're going to point in the same direction. Okay. Remember that we cared about regular momentum because there was a conservation law. That is, if the external force is 0, then this implies that momentum is conserved, right? Momentum is constant. In other words, momentum is constant when there's no external forces. We're going to have an exactly analogous conservation law for angular momentum, and that's why we care about angular momentum too. In this case, we're going to use the rotational version of force, that is torque. And when the total torque, external torque on an object is 0, then angular momentum is going to be conserved as well. Okay? In other words, if there's no external twisting forces on an object, the angular momentum will be constant. It will not change. So what this means is that if you measure the initial angular momentum and then some stuff happens, and that stuff cannot include external torques, so there's no external torque during this stuff, and then you measure the angular momentum at the end of this, those two have to be equal to each other. If we use our definition from here, I omega, this tells you that the initial moment of inertia times the angular velocity, the initial angular velocity, has got to equal the moment of inertia times the final angular velocity. Now this looks really boring, right? This just looks like, well, if nothing happens here, then omega final must be equal to omega initial. But remember that I tells you about the distribution of the mass. And the distribution of the mass can change. This is completely unlike regular momentum. With regular momentum, you cannot have an object moving with some regular momentum, and then the mass shrinks, and then the velocity increases to keep the momentum constant. That cannot happen. It doesn't even make any sense. That actually can happen with angular momentum, right? So we have to include the moment of inertia in our thought process when we're thinking about what's changing. Okay, let me give you an example. The quintessential example here is when you have a figure skater and she's spinning around on ice like this. And she's got some rotational velocity, and she's got her arms and her legs spread out, and she's spinning around on ice. Because she's on ice, there's no external torques, so angular momentum is going to be constant. When she's like in this configuration, her moment of inertia is very large. Then she'll bring her arms and legs close to her body, and so that will look like this. And then this will be close to her body, like this. I will shrink, but what happens if angular momentum is constant, that means that her rotational velocity must increase, right? So she must have a small angular velocity in beginning with a large moment of inertia, and then a small moment of inertia with a large angular velocity, right? These must be sort of compensating for each other in exactly the right way to keep angular momentum constant. And you see them do this actually all the time, not just standing on the ice and then let me speed up. They do this whenever they're preparing for a jump, right? They're getting ready for a jump. They'll give themselves a little bit of rotational velocity. Their arms and legs are spread out wide. Then they launch themselves into the air, and as soon as they do that, they'll bring their arms and legs into a tuck to decrease the moment of inertia, increases the angular velocity while they're in the air so they can get as many rotations as possible because they want to get that triple axel completed. And then before they land, they will spread their arms and legs out wide, increase the moment of inertia, decrease the angular velocity, and then they can land. And the reason they want to decrease the angular velocity is because they want to keep control of the situation, right? They're trying to control and not fall, right? And so, and you see this occur with not just figure skaters, but anyone who's doing any kind of rotational stunts, divers, snowboarders, any situation where there's some rotation, you'll see them control their rotation rate, omega, by controlling their mass distribution, the moment of inertia. And the whole time they're relying on angular momentum conservation. Now that's not the way they talk about it, but that's what's happening with physics behind the scenes with their bodies. They rely on this to get the stunts to work.